Dear students, today I am going to start another new topic which is Ramachandran Plot. It is from biochemistry and related to protein structures. So, what is Ramachandran Plot? Before telling you about Ramachandran Plot, I am going to tell you about its principle or the fact on which it is based. And there are few definitions also which you need to know before you understand any such plot. So, spatial arrangement of atoms in a protein is called a conformation. Actually, this refers to a structural state that can, without breaking any covalent bond, interconvert with other structural state. A change in conformation could occur, for example, by rotation about single bond. Of the many innumerable conformations that are theoretically possible in a protein containing hundreds of single bonds, one generally predominates. This is usually the conformation that is thermodynamically the most stable, having the lowest Gibbs free energy. Gibbs free energy is denoted by capital G in thermodynamics. Proteins in their functional conformation are called native protein. Now, what are peptide bonds, for which Ramachandran Plot explains certain things? The peptide bonds uh, and its stereochemistry. So, Linus Pauling and Robert Corey in 1950s worked on protein structure. Their first focus was on the structure of the peptide bonds. It is known that all the proteins are made of L amino acids. This fixes an arrangement at the alpha carbon. And this is alpha carbon. Alpha carbon of adjacent amino acids are separated by three covalent bonds. Arrange C alpha, uh, wait here, C alpha, C, Cn, and then again C alpha. So this is how this arrangement exists. X-ray diffraction studies of crystals of amino acids and of simple dipeptides and tripeptides demonstrated that the amide CN, amide CN, this one, amide CN bond in a simple amine, and that the atoms associated with the bond are coplanar. Amide CN in a peptide is somewhat shorter than the CN bond in a simple amine. That the atoms associated with the bond are coplanar. This indicated a resonance of partial sharing of two pairs of electrons. Resonance of partial sharing of two pairs of electrons between the carbonyl oxygen and amide nitrogen. Carbonyl oxygen is here, amide nitrogen is here, and electrons are being shared here from here to here, and that is why it is carrying partial negative charge and this is carrying partial positive charge. The oxygen has same thing, that oxygen has partial negative and nitrogen has a partial positive charge, setting up a small electric dipole. So when this kind of charge are distributed and present a little far away from one another, they form a electric dipole. The four atoms of peptide groups lie in a single plane. फोर एटम्स कौन से हुए? O, C, N and H. These four lie in a single plane, as you can see here. This is the plane O, C, N and H. These four lie in a single plane. This arrangement is like that. The oxygen atom of carbonyl oxygen and the hydrogen atom of amide nitrogen are trans to each other. You can see here, this is transposition. So these are trans to each other. From these studies, Pauling and Corey concluded that amide CN are unable to rotate freely. Amide CN, this CN, is unable to rotate freely because of their partial double bond character. You can see that here also partial double bond character is shown. And in this resonance, at some time double bond is here, while other time double bond is here. So because of presence of this partial double bond character, these occur in a rigid plane, and then this bond cannot rotate freely. CN bonds make 1/3 of all bonds in backbone of polypeptides. Now these bonds are present in the backbone of polypeptide. Other single bonds in the backbone may also be rotationally hindered depending on the size and charge of the R group. अब R group कहाँ है? Again you see here R group. R group कितना बल्कि है, कितना बड़ा है और कितना छोटा है, इसके हिसाब से वो भी इन दो प्लेन्स के बीच में कैसे एडजस्ट कर रहा है, ये अलग अलग है हर एटम के लिए, हर अमीनो एसिड के लिए. Virtually all peptide bonds in proteins occur in this trans configuration, leaving one exception. Now, the backbone of polypeptide chain can thus be pictured as a series of rigid planes separated by substituted methylene groups CHR. CHR बीच में है इनके, और ये रिजिड प्लेन्स जो हैं एक के बाद एक के बाद एक के बाद लगे हुए, जैसे जैसे जितना भी बड़ा ये पेप्टाइड है. Rigid peptide bonds limit the number of conformations that can be assumed by a polypeptide chain. हर दो अमीनो एसिड्स के बीच में क्या पॉसिबल एंगल हो सकता है, कैसे ये रिजिड प्लेन एक दूसरे के ऊपर एडजस्ट हो सकते हैं, वो यहाँ पे डिपेंड करता है कि आर ग्रुप कितना बड़ा है, उसको अपनी जगह चाहिए. अब जब ये आर ग्रुप यहाँ पे कितना बड़ा है, इसकी बेसिस पे इनका आपस का अरेंजमेंट तय है. तो अल्टीमेटली फिर पूरी चेन में हर दो अमीनो एसिड्स के बीच में आर ग्रुप कैसे एडजस्ट हो रहा है और ये प्लेन्स आपस में कितना शिफ्टेड है, उसके बेसिस पे अल्टीमेटली पॉलीपेप्टाइड चेन का क्या कन्फॉर्मेशन होगा, क्या शेप आएगी, वो तय होता है. Rotation is permitted about C and N bond. N dash C alpha, N dash C alpha के बीच में और C alpha C. By convention, the bond angles resulting from rotations are labeled as phi and psi. Phi is for NC alpha and psi is for C alpha C. The freedom of rotation on each side of the peptide unit is equally important because it allows proteins to fold in many different ways. By convention, both phi and psi are defined as 0 degrees in the conformation in which the two peptide bonds connected to a single alpha carbon in the are in the same plane. ये कंफर्टेबली जिस एंगल पे डिफाइन रह पा रहे हैं दैट इज द 0. In principle, phi and psi can have any value between -180 to +180, but many values of phi and psi are prohibited by steric interference between atoms in the polypeptide backbone. Now ये यहाँ पे है ग्रुप आर ग्रुप है, वो यहाँ से इंटरैक्ट करेगा, इधर से इंटरैक्ट करेगा, एंड इट मस्ट हैव इंटरैक्ट मीन्स इट मस्ट हैव इट्स ओन स्पेस. तो ये जिस डिस्टेंस पे स्टेबली रह सकता है उतना डिस्टेंस ये प्लेन्स उसको देंगे. इसलिए इसके अराउंड ये प्लेन भी शिफ्टेड रहेगा, ये प्लेन भी शिफ्टेड रहेगा, जिससे कि ये ग्रुप यहाँ पे हो सके, रह सके. The conformation in which phi and psi are both 0 degree is prohibited for this reason. अब बिल्कुल एक दूसरे के ऊपर तो आ नहीं सकते, इसलिए 0 तो हो नहीं सकता. कोई ना कोई बॉन्ड एंगल इनके बीच में होगा जरूर. This is used merely as a reference point for describing the angles of rotation. 0 कहा कि ये इसके ऊपर है तो 0 है, तो दिस इज द रेफरेंस पॉइंट. अब इससे ये कितना शिफ्टेड है, कितना शिफ्टेड है, ये इसके डिफरेंट बॉन्ड एंगल्स तय करेंगे. एवरी पॉसिबल सेकेंडरी स्ट्रक्चर is described completely by the two bond angles phi and psi that are repeated at each residue. Allowed values for phi and psi can be shown graphically by simply plotting phi versus psi, an arrangement known as Ramachandran plot. Now we are coming to main topic. This was the basis of Ramachandran plot. Whatever I have told you till now makes the basis for Ramachandran plot. The Ramachandran plot shows the conformations permitted for most amino acid residues. The conformation of main chain of polypeptide is fully defined when phi and psi angle for each amino residues are known. Now we come to main topic. This is Ramachandran plot. Here on this coordinate they are showing phi angle, and here they are showing psi angle. Again in this coordinate this is minus phi and plus psi. We can read from here also. In polypeptide main chain N C alpha and C alpha bonds relatively are free to rotate, which I have already told you. These rotations are represented by torsion angles phi and psi respectively. The full name of the scientist was Mr. Dr. G.N. Ramachandran, who used computer models of small polypeptides. उन्होंने कैसे एक्सपेरिमेंट किया और कैसे डिसाइड किया कि हर दो अमाइनो एसिड्स के बीच में क्या फाई और साई एंगल रह सकता है. सो ही यूज्ड कंप्यूटर मॉडल्स ऑफ स्मॉल पॉलीपेप्टाइड सो टू सिमेट्रिकली वेरी फाई एंड साई with the objective of finding the stable conformations. For each conformation, the structure was examined for close contact between atoms. You can see so many atoms are here. So it was necessary to find out how far these two are, and these calculations were done to define the correct place of each amino acid when any two are linked in a polypeptide. Atoms were treated as hard spheres with dimensions corresponding to their van der Waals radii. Therefore, phi and psi angles which cause spheres to collide correspond to sterically disallowed conformations of the polypeptide backbone. इस बैकबोन में सी एन सी एन अल्फा सी अल्फा सी एन this is the backbone of polypeptide chain. Now if this is amino acid 1, this is amino acid 2, then between these two what will be the phi and psi angle, that is at what angle they will provide space to this R group. Similarly here, so all the spaces will be different because this amino acid is different, this amino acid is different, and this is also different, or these are same also, but how far they can exist to give the space to this R group. In the diagram above, white areas, you can see so much white areas here, correspond to conformations where atoms in polypeptide come closer than the sum of their van der Waals radii. वो बहुत पास आ रहे हैं. These regions are sterically disallowed for amino acids except glycine, which is unique in that it lacks a side chain. ग्लाइसिन में कोई साइड चेन नहीं है, इसलिए उसमें स्टेरिक हिंड्रेंस नहीं होगी. ये अगर किसी पॉलीपेप्टाइड चेन में है तो इसकी वजह से फ्लेक्सिबिलिटी या अगल बगल के अमीनो एसिड्स को मूव करने की फ्रीडम ज़्यादा होगी, स्टेरिक हिंड्रेंस नहीं होगी. द रेड रीजन्स करस्पॉन्ड टू कन्फॉर्मेशंस वेयर there are no steric clashes. Let us see the red regions. These regions, these are allowed regions, namely the alpha helical and beta sheet conformations. The yellow areas, the allowed regions, show the allowed regions if slightly shorter van der Waals radii are used in calculation. That is, the atoms are allowed to come little closer together. This brings out an additional region which corresponds to the left-handed alpha helix. Yellow region में left-handed alpha helix possible है. I think you know the secondary structures. That is why you must be understanding left-handed alpha helix क्या है, beta sheet क्या है, and right-handed alpha helix क्या है. All amino acids cannot form extended regions of left-handed helix, but occasionally individual residue adopt this conformation. These residues are usually glycine but can also be asparagine aspartate, where the side chain forms a hydrogen bond with main chain. एस्पार्टिक एसिड एस्पार्जीन ये जो है ये एसिडिक अमाइनो एसिड्स हैं, तो इनका बगल के बैकबोन से भी हाइड्रोजन बॉन्डिंग हो सकती है, इसलिए फिर उनका और अमाइनो एसिड से अलग बिहेवियर हो सकता है. Therefore stabilizes this otherwise unfavorable. तो in practice right handed alpha helix is seen mostly, but कहीं पे asparagine है, aspartate है या ग्लाइसिन है, तो ग्लाइसिन कोई स्टेरिक हिंड्रेंस नहीं दे रहा है, इसलिए लेफ्ट हैंडेड हेलिक्स दिख सकती है स्ट्रक्चर में. बट यहाँ पे क्या है कि ये ऑपोजिट साइड में लेफ्ट हैंडेड दिख सकते हैं एस्पार्जीन और एस्पार्टेट, बिकॉज दे they are stabilized in that position also because of the binding with the backbone in hydrogen bond. The three helixes occur close to upper right of alpha helical region and is on the edge of allowed region indicating lower stability. Yellow region lower stability show कर रहा है जहाँ की left handed helix possible है at the given phi and at the given phi and psi angles. Disallowed regions usually involve steric hindrance between the side chains, C beta methionine group and main chain atom. Glycine has no side residue, therefore can adopt phi and psi angles in all four quadrants of Ramachandran plot. Hence, it frequently occurs in turn regions of protein where any residue would be sterically hindered. Now, ग्लाइसिन में साइड चेन नहीं है, इसलिए कोई स्टेबल स्ट्रक्चर बनाने के बजाय अभी हम जब मोटिव्स एंड पैटर्न्स पढ़ेंगे तो उसमें हम देखेंगे कि मोटिव्स के लिए टर्न्स जरूरी हैं, स्ट्रेट चेन ही नहीं जरूरी है. एक स्ट्रेट चेन का रीजन है, फिर वो टर्न होके फिर से उल्टे डायरेक्शन में ऊपर के डायरेक्शन में दूसरी चेन चल रही है स्ट्रेट, तो ये जो टर्न है या लूप है वो लूप में ग्लाइसिन एस्पार्जीन एस्पार्टेट इन सब के होने की वजह से या प्रोलीन के होने की वजह से वहाँ पे फिर अल्फा हेलिक्स या बीटा शीट नहीं बन पाती है, as a result of which turns carry these amino acids and these are also important for folding patterns. So this was all for uh, today, and this is all about Ramachandran plot. I hope I am very clear about every aspect of this polypeptide chain and these phi and psi angles. If you like my video, then please like it, share it, and keep watching my videos. Thank you.